Oh, good morning, everyone. Welcome to our pre-lab lecture. Today we are going to look at experiment on determination of Avogadro's number. I know everybody knows about Avogadro's number. You have used that before. Let me share my screen so that you can see my whiteboard regarding what we are going to do today, the determination of Avogadro's number. Now, the number we are talking about here is the 6.0 6.022 times 10 raised to positive 23. Avogadro's number represented by or denoted using the symbol Na, all right, Na with the subscript capital A represent Avogadro number with this numerical value to positive 23. And some others uses the three significant figures. I don't know why you can see my whiteboard for some reason. You can see my whiteboard. Let me see what's going on here. You should be able to see. Wait a minute. Let me just make sure you can see my whiteboard. Yes, that is the Avogadro's number 6.022 times 10 raised to 23. There is what we call mole day. This represent number of things, and it was going from the number of carbon atoms in 12. These represent number of carbon atoms in 12.01 grams of carbon. Avogadro worked with different gases and he ended up with this numerical value of number of carbon atoms in 12.0. We call this Avogadro number. You have used this before. It is a unit used by scientists to represent number of things that 1 mole, all right, 1 mole represent Avogadro number of things times 10 raised to 23 atoms or particle, all right. This is a unit used by scientists to represent number of things. An Avogadro number of things is called a mole. Avogadro number of items or atoms, molecules represent 1 mole of what you are referring to in terms of here. So if I have 1 mole of students, all right, if I have 1 mole of student, I have this number of students in my class, whatever you are counting for. What you want to commit to your memory is relating the mole, all right, atoms and the atomic mass on the periodic table. There is here when we talk about element on the periodic table, element like that, anything you can think of on the periodic table. 1 mole, all right, 1 mole of that element, 1 mole of an element equals to Avogadro's number of what? Avogadro's number of atoms. 3 atoms, 23 atoms equals to atomic or atomic mass over here, the mass, let's say just here, the mass on the periodic table. mass on the periodic table, and it's represented using grams per mole, units for mass for an element. For example, e.g. here, e.g. 1 mole of sodium, an element on the periodic table, represent or has this number of atoms times 10 raised to 23 atoms of what? Atoms of Na, sodium, which is equals to on the periodic table 22.9898 grams, and this is grams per mole, the unit, which means 1 mole. I get this number from the periodic table. You don't have to memorize. You'll be given the periodic table. All right, you'll be given the periodic table. You don't need to memorize the atomic masses. What you have to do is look at the element. All right, you know from the periodic table how to read the what the numbers represent. All right, this is 22.9898, how to find the atomic mass. This is for an element, just an element on the periodic table. Now for a compound, all right, compounds, that means when two or more elements combine to form a compound in a specific ratio, we use the same approach that 1 mole of a compound contain, it could be formula units, all right? If it is ionic compounds, they will talk about the formula units. Or if it is molecular compound, you say molecules, which is equals to molar mass. And to get this part right here, you use what? Use periodic table. Use periodic table to find the molar mass by finding the sum of each. All right. Atomic masses are for each element in a compound. You use the periodic table, look at the atomic mass of each element on the compound. You find the sum of that, that gives you the molar mass. It's grams per mole. E.g., let's see an example here. When you're dealing with a compound, how do you relate the mole to molecules to molar mass? A simple compound such as H2O, all right, we can say 1 mole of H2O, all right, 1 mole of H2O contain Avogadro's number of molecules, 23 molecules of H2O. You say molecules, not moles. There's a difference between molecules and moles, which is equals to 18.02 grams of H2O. Where I'm getting this 18.02 is taking the atomic mass of one hydrogen of the periodic table, multiplied by 2, and add for 1 oxygen. This gives me 18.02. This is how you relate the mole, all right, Avogadro number, and the molar mass of a compound. When you're dealing with a compound, this changes. But when you're dealing with an element, that's a single element of the periodic table, you just have to put the atomic mass of the periodic table, Just to give you, general idea, because the quiz will revolve around, using dimensional analysis to find the number of grams, to find the number of moles, to find the, the number of molecules and so forth. And those two equivalent statements you will use to generate conversion factor to change from moles to molecules and vice versa. I don't want to get in details into that. Let me just dive into determination of Avogadro number. The calculation you will use today is to crunch out numbers, and at the end, you will end up with the value or numerical value for Avogadro number. We always do this in the lab, but since this is a remote instruction class that's online, We will only have to see the simulation and walk you through the experimental setup and show you where the numbers come from. So the objective for this, let me just zoom on my slide here. The objective is to determine the Avogadro number here, all right? Find the number of molecules in the units. The units will be, all right, molecules. The unit will be molecules per mole, all right? If this is the unit, if this is the unit of our Avogadro number, that means we need to find the molecules and we need to find the number of moles, all right? And when we divide by, we divide the two numbers. At the top is the number of molecules, at the bottom is the number of moles. And if we have those two numbers, then we are set to calculate the Avogadro's number. It may sound, you know, straightforward, but there are some steps you need to, or we normally do. In part A is to find the number of moles, and in part B is to find the number of molecules in what we call monolayer. Normally, we use a watch class to determine a monolayer. A monolayer, from the word mono, that means spreading out steric acid. All right, we normally have a watch class. This is a watch class. You know what the watch class is. I'm holding a watch class before me. This is called a watch class. Maybe some of you have seen in a lab setup. And the first thing is to find the number of molecules on monolayer. That means having one layer of steric acid, so that if we know the number of number of molecules, we divide by the number of moles of steric acid, and then we have the values for Avogadro number. So the experimental setup here, all right, this is a watch class, and a watch class we normally fill with DI water, and the steric acid form a single layer on the surface of H2O. This is the molecule of steric acid, and it has what we call polar tail and polar head. Polar head means it has a positive negative terminal. This means the molecule has no polarity in it. That means the electrons are uniformly distributed. This end will dissolve in H2O, but this one will just form a layer on the surface of H2O. What you see here saying 1XS is when you drop a single drop on the surface of water, you will not see anything. It will just dissolve. It will form a single layer until when it completely form a layer on the surface of H2O. With one excess drop, it will appear as a clear lens, and then it tells you that you have a uniform single layer of steric, all right, of steric acid on the surface of H2O. We will need to know the surface area of the monolayer, all right? The purpose of this is to know the surface area. Surface area, there is an equation we will be using, and you're gonna be using that to find the surface area. Here is the equation. Assuming this is your experimental setup, all right? Using the a dropper, you don't have the dropper with you. This is the dropper. You add 1 drop, 2 drops, 3 drops until you count how many drops you use to form a monolayer. We need to find the surface area of the monolayer using this equation, please. This document is on the module on determination of Avogadro number. I posted this last week, so if you are wondering where is he getting this handout or information, it is available online. So Example exercise 11.1 is calculating the molecules in monolayer. We need that so that it will be our numerator. Look at my white board. We need to find the number of molecules, which will be at the top. And to calculate the number of molecules, you will proceed via this, via this equation. Pi d, all right, square over 4. This is, pi is the numerical value, 3.14 for mass. You know what pi is. That's the numerical value for pi. And d is the diameter. You are wondering where are we getting the diameter? We normally measure the diameter using a meter ruler, metric ruler. It's a metric ruler, which is, you know what a diameter is. I'll show you where to get that value. And 4 is a constant. This will give us the area of the monolayer, all right? Area of the monolayer. So if you have your area in centimeters square, because you're gonna use units, you have millimeters and centimeters. You will use centimeters and area centimeters square. There are, here we want to know how many molecules per monolayer. How many molecules per monolayer? In other words, how many molecules do we expect to have in a monolayer like this? In a monolayer like this, assuming that we have a monolayer, the surface of a wet class. With your area, you see this 165. Once you will determine this surface area of your monolayer, I will substitute where I see 165 on work example 1 with your area. You will determine, you will use this equation. Your diameter will change. I'll give you the diameter. It's right here. Let me just even, so that we are on the same page, I can be hitting at the same time going through the data sheet so that you know. Allow me to fast forward to where data sheet is, finding the, here, part P right here is, part P right here calculating the number of molecules. So I'll come back to A. So if you know the diameter, you see this diameter of the watch class. This is your data sheet, by the way. What you see below here is the data sheet online. And the purpose of this is to, I've measured the watch class. So I measured the watch class, pre-filled the data sheet for you. And this is the diameter of the watch class. This is your diameter. You're gonna plug it in this equation to find the surface area of the monolayer. So pi times your diameter, which is 13.9 centimeters square. Centimeters, and 4 is constant, and it will give you a value other than 165. All right, other than 165. Let me just any question on finding the surface area? Any question before I proceed? So you have what? You have the diameter 13.9. Plug it in this equation right here to give you the surface area. It will be other than 165 you see on the data sheet. Now, the subsequent calculation here is to find the number of molecules per monolayer. It turns out that one molecule, this is, all right, this is the area of one molecule in nanometers square. And the conversion you have here is, if this is your area, it's gonna change per monolayer. What you start off with is your area of the monolayer. The conversion, everything including this is conversion 1, 2, 3, is to find the number of molecules. It's the same thing. If you don't want to use this, the subsequent run here is the same thing. You can ignore this one and use this one right here so that you cancel out the units. I like the second one. I like the second one. Because this one half square, you may miss to key in on your calculator. I know some of you, you may have difficulty figuring out. Please learn if you are familiar with your calculator. If you haven't used your scientific calculator, well, I'll practice with this first to see if I'm getting this value. If you are not getting this value from this worked example, then something is wrong with how you key in your calculator. So I'll practice with this first to make sure I know how the key works of my calculator. So with the area, all right, with this area of 1 molecule of steric acid, is the same thing here. You should be able to calculate the surface area of this number of molecules per monolayer. So in B, show your calculation. You may print out, use pen and show your work here below on how to find the number of molecules of monolayer. Are we together? So far, so good on finding the area, the number of molecules, sorry. Finding the area and finding the number of molecules. And please write molecules per monolayer because I'm just going to be looking at the units. This is, this will give us the what? This will give us the top part. This will give us the top part. Once we figure it out the number of moles of, once we figure out the number of moles of, I mean molecules per monolayer, we need to find the number of moles. We need to find the number of moles. And initially, you have to take account of number of, or first here, there is what we call calibration of pipette. Pipette is, you know, pipette is, this is pipette. You may have seen this in your lab kit. Calibration is to determining how many drops makes up 1 ml. In other words, we'll take a graduated cylinder and then we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then once we get to 1 ml, if this is the graduated cylinder, all right, this is graduated cylinder, maybe 10.0 ml graduated cylinder, all right. If it takes here to get to 1.00 ml, how many drops of H2O? This is what we call calibration, and in the handout, it takes 65 drops. In other words, why are we calibrating this? So that we know one, or determine how many drops makes up 1 ml. If we know how many drops make 1 ml, we can convert how many ml we use to find the monolayer of steric acid. For example, to know the volume of steric acid, if it take me, let's say, 12 drops of steric acid to form a monolayer on a white class, 12 drops of steric acid to form a monolayer, I will use the calibration information here that if 65 drops actually give me 1 ml, then how many ml are in 12 drops used to make the monolayer? And that is what is taking place in calibration right here. We will come back to A here. Let me just show you. Look at the data sheet here. Why we had to do in A is calibrating the pipette. Calibrating the pipette is to know how many drops makes 1 ml. And the numbers you see here, all right? The numbers you see here, I had to do three trials, all right? 3 trials in the sense that this is 65, this is 64, this is 66. That means the first time I count 1, 2, 3, 4, 5 until 65, I have 1 ml. The second time to get that, I have 64. The third time, I have 66. I'm trying to hit 1 ml mark on graduated cylinder. And of course, you know how to find the average, right? Show me your work. Please do not, all right? Do not just use your calculator and give me a value here. This is the average of, drops of DI water used in calibrating the pipette. With that, you will write down the number of drops per ml here. We will use that to find the number of molecules. That will be handy in now determining this value, all right? We want to know this value here. This will be used in finding the number of moles, and I'm going to show you on the handout how that works. This one right here, moles, all right? This is the number of moles in a monolayer. How many moles did we use to make this monolayer? That means the single service. I don't mean to go back there, but we want to know how many moles. Am I seeing something different? My whiteboard is not responding with, my whiteboard is frozen again. I'm advancing and you can't see what I'm seeing on my whiteboard. Let me just unplug it again and see if it's gonna communicate. All right. We want to find the number of moles. All right. We want to find the number of moles in monolayer. All right. Right here on my whiteboard, not whiteboard, but slides on the right. This value here is the number of molecules in a monolayer. This is from part A. Number of molecules in part A. And right here, this drop here is from the number of drops you see here corresponds to how many drops did we use to form a monolayer. That means we had to add 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, 12, maybe 11. By the 11, we see a clear lens. That means we have formed a monolayer. We stop. It takes 11 drops to form a monolayer. This is 11 drops to form a monolayer. In our case, in the data sheet, which you will have to work with, let's see how many drops did it take to make a monolayer. All right. I had to do 3 times. These are the number of drops. These are the number of drops. All right. Number of drops per monolayer. Number of drops per monolayer, 11. There is 11, all right, 11, 10, and is it 12? No, 9, 10, 11. These are the number of what? Number of drops to get the molecules. If it took 9 drops, look, 9 drops to form a monolayer, how many molecules per monolayer? The drops here is from the calibration. This is from this value here. You're gonna find the average right here. Once you get the average drops right here, once you find the average right here, it will be your average. You're gonna use that. How many drops per ml? It is your second conversion factor. This one, you have 1.48 grams. I have given you also that in the data sheet. Should use this value. You see this from the instructor. This is the grams or mass of stearic acid per ml. In 1 ml, this is the mass of. So I have to count how many. 1 ml of stearic acid weighs how much. It's the same thing here, except instead of 1.4, yours will be 1.64, and the molar mass of stearic acid is the same. So you're gonna use the same molar mass. This is the molar mass of stearic acid. We are using stearic acid. Look at A. We're using stearic acid. The molar mass is the same. It's not gonna change. This will give you molecules per monolayer, moles per monolayer. This is moles per monolayer, not molecules. Part A is molecules. This is moles. You'll see this, you'll have to do 3 times. The first time is instead of 11, it's gonna be 9. Instead of, yeah, it's gonna be 11, so probably you're gonna get the same 5. No, not the same, because this will change. This value you will substitute with what is highlighted here, all right? This value will be substituted with what I do have right here. You'll do the same thing for 10, that's gonna give you that. And then this concentration right here, this one, don't worry about this value is this. So already given that. And once you have for this, you'll have now what it takes to calculate the Avogadro number here. Let me enlarge this so that at least we see. You can see clearly here that once you do the calculation for each, all right, each trial, all right, you will now calculate Avogadro number for each trial. You will calculate Avogadro number for each trial. That means the molecules for 9 drops, for 10 drops, for 11 drops. Avogadro number is the number of molecules in part A over the moles. Once you know the number of moles, all right, once you know the number of moles, you will divide. Let's see on the worked example, determining the Avogadro number now is the number of molecules all over the number of moles, and this will be the unit moles per, or molecules per mole, sorry, molecules per mole, which is in the same neighborhood so long as you are in the domain of, you know, 2 power positive 23. It doesn't really matter, you know, close to that, it's acceptable. The true value is 6.02, but here is 9.5. It's okay if you are in 10 to positive 23. If this was 10 to positive 15, that's a huge difference. If this was 10 to positive 30 or negative, whatever you have here, that means there's something went wrong. So that's what you will do for each trial. If you know the number of molecules, number of moles, you'll find the Avogadro number, and then you find the average of the 3 Avogadro number, and then it's placed there, and that will be it for, you know, for the number of molecules. I want you to answer the questions, or before even I go through the questions, is there any question on how to find the Avogadro number? You can use the chat feature. Any question? Any question on how to find the Avogadro number? I've given you the calculation already. It is pre-filled for you. The data sheet is pre-filled for you. You don't need to do anything. Any question on how to find the Avogadro number? Remember, the objective is to get 2 numbers. One is the molecules at the top and moles at the bottom, and then you divide the 2 numbers to get your numerical value for Avogadro number. Any question? No question? Actually say no. So I believe if you have no question, let me just go back to data sheet. On data sheet, I want you to answer the pre-lab. There is pre-lab, you'll read the background. I didn't read everything. You read the background so that you are in a position to answer the questions on the pre-lab. For example, here, you can use the terms down here, select molar mass, you know, to fill in the information you have here for these questions. You read the background to understand the circle, the portion which is dissolved in water. Unless you read the background, you're not going to understand this. So I want you to read and understand the, you know, what's all about. To answer question 5, there is YouTube, about 7 minutes, which I recommend you to watch. Still on determination of Avogadro number. I know you can watch at your own convenient time, about 7 minutes. And somebody in there mentioned about possible errors you will encounter, or you may encounter in this experiment. All right. What example will help you on how to proceed with this? All right. You got to see the worked example, and there is pre-lab. This is the data sheet, what you are seeing right now. This is the data sheet which I went through. Let me just go through some of the calculation here. Question 3 here, calculate the what? Calculate the mass of water that contains these molecules. I went through this at the beginning. Look at, let me just minimize this right here. There is, and I don't know why my whiteboard is acting up this morning. Did I not act right? I mean, connect right? Let's see. Yes, this is what I was talking about, that for this problem here, calculating the number of molecules, question 3. Question 3 here, look at the question 3. Let me just bring this up on Word document. If you look at question 3 here, calculate the mass of molecules. You cannot be using on my whiteboard this, the Avogadro number. This is a compound right here. What I'm circling is you generate the conversion factor by using dimensional analysis. Again, it's not responding. For some reason, it's not responding again. But nevertheless, what you need to do is the using Avogadro's number and the mass of H2O. At this point, you are expected to write the chemical formula for H2O, find the molar mass of H2O, and say Avogadro number of H2O weighs this much. That is the molar mass I gave you. This is for an element. You'll see later on for the compound. Here, let's see. Calculate the molecules in 1 liter of a standard temperature pressure. Let me just try again and see if it's gonna communicate. Maybe I need to see if I can get that. Condition at STP. At STP, at standard temperature pressure, 1 mole of any gas of a gas. In this case, 1 mole of a gas, 1 mole equals to 6.02 times 10 raised to 23. All right, equals to 22.4 liters at STP, at standard temperature pressure. So here, all right, if you have 0.0, this should be right here. This should be ozone. Calculate the number of molecules in 1 liter of ozone. This is O3. That is O3. And 1 mole of O3, all right, ozone, 1 mole of O3 contains these molecules of O3, which will occupy that. If 22.4 liters equals to 6.0, all right, 6.02 times 10 raised to 23, 1 liter equals to what? That is the question. Probably, maybe some of you are wondering what this means. At standard temperature pressure, this is a condition. And of course, you know what temperature should be, 278, 298. Pressure is 1 atm, all right? These are conditions at what? At standard temperature. pressure, STP. Now the follow-up number 3 is the same thing. This is ozone gas. You have to find the number of molecules in 1 gram. Of course, with that, 1 mole of O3 weighs, all right, weigh 48.0 grams. And it has what? It has Avogadro number times 10 raised to 23 molecules. You have to relate now that the molecule 1 gram. This is ozone again, all right? Subscript right there. This is a subscript. This is ozone. So 1 gram, if you know from here, look at my whiteboard, 48 grams contain these molecules of O3. So 1.0 grams of O3 times, you want to get rid of grams of ozone. You are looking for molecules of O3. This is Avogadro number times 10 raised to 23. This is this is 48.0, and then grams and grams go away. You plug it in your calculator and you end up with that. That's how you do this. Probably maybe you are not covered that. Still, it's a general knowledge they expect you to understand. All right. And then lastly here is calculate the mass of 1 molecule of ozone, 1 molecule expressed in grams. Again, this is ozone. All right. This is the mass of ozone. And what that means is Avogadro number of molecules, 23, weighs 48.0 grams of O3, 3 oxygens. What about 1 molecule? They are talking about here 1 molecule. Look at what I'm highlighting, 1 molecule. If Avogadro number, look at the whiteboard, if Avogadro number weigh this, how about 1 molecule? And then you know how to set up your equation. And that will be the follow-up question. The follow-up question. Having said that, that is just only the exercise for this determination of Avogadro number. There is a YouTube, link on determination of Avogadro number under the module for this exercise. There will be a quiz revolving around this exercise, which is due on Sunday, all right? And that marks the end of today's pre-lab lecture. Is there any question before I stop sharing the screen? Any question? Any question? Ashley say, I don't know if they Ashley's response is for previous question. Any question? Oh, Angela say no. So if there is no question, please, I know you may have received invitation to do the survey of the course. Please do that. I'll also send you a reminder that please kindly do the survey of the course before the end of the semester. Other than that, thank you for tuning in this morning. I'll see you again Monday. Same time, we'll be doing experiment on single replacement reaction. It's not something new to you. Please read the background again. I'll send more information on that. And I believe you have the chemical reagent in your lab kit. Other than that, have a good morning. Be safe. I will now stop sharing my screen and end my